In this final video on the crystal chemistry of ionic materials, we look at the perovskite structure, one of the most important crystal structures in materials research. We'll see the structure is based on the close packing of layers that contain an ordered arrangement of anions and larger cations, and the smaller cations occupy the octahedral interstices between those layers. When the layers are cubic close packed, we obtain the cubic perovskite structure, where the corner sharing of the octahedra enables considerable structural flexibility and allows the design of perovskites with an almost unlimited number of different chemistries and a myriad of different functional properties. We'll also look at perovskites where those close packed layers are hexagonally close packed, and that produces structures with one-dimensional chains of face-shared octahedra. I hope you will enjoy it.
We're now familiar with ionic structures which are based on close packed arrangements of anions, and the cations, which are smaller, occupying tetrahedral or octahedral sites. We now look at a set of structures where the close packed layers don't just contain anions, but they also contain cations. Now in these cases, the cation in the layer, shown in red here, must be a larger cation, such that it's size matched to that of the anion, otherwise close packing couldn't be expected. So for oxides, where the oxygen anion has a radius of about 1.4 angstroms, we'd be thinking of larger cations such as those from group 1, sodium, potassium, cesium, rubidium, but not something like lithium, which is too small to be compatible with oxygen within this close packed layer. Group 2, barium is commonly found in these mixed cation-anion close packed layers, and indeed its radius is almost identical to that of oxygen. And also some of the larger 3+ cations in the lanthanide series. All of these provide a good fit, and in this case it's possible to think of the structure being assembled from this close packed cation-anion arrangement. The one I've shown here, and I've outlined the two-dimensional repeat, has a composition AO3, where A is the generic term I'm using for that larger cation. And so for every cation within the close packed layer, there are 3 oxygen anions. These mixed anion-cation close packed layers are the basis of the well-known perovskite structure, arguably one of the most important structures encountered in materials research. The perovskite structure is built of these AO3 close packed layers. The presence of the cations in the close packed layers reduces the number of possible interlayer octahedral sites that would be coordinated by 6 anions. So for a close packed layer we've seen before, where all of the species in the layer are anions, then we're familiar with a 1-to-1 ratio of the octahedral positions, shown in blue here, just showing the base of them. Now in the layer where I have an ordered arrangement of large cations and anions, some of these octahedral positions are blocked. And by that I mean, for example, here, the base of this interstice, here's our 3 large spheres, but one of them now is a cation. And so if a smaller cation was to occupy this interstice, it would no longer be coordinated by 6 anions. It would have at least 1 large cation as its neighbor, and that is not favorable. So now in green, I show those octahedral interstices where one of the neighbors is the larger cation, but for the ones in blue, the interstice still has at the bottom of the octahedron 3 neighbors, and if we put the next close packed layer on top, it would have 3 more anion neighbors. And so now we see the remaining potential octahedral sites that would be coordinated by 6 anions. Let's just show the base of that octahedron. It's possible for a smaller cation with the appropriate radius ratio to now fully occupy these remaining anion octahedra. And if they do, then our stoichiometry, we already have AO3 for our close packed layer. There's 1 B site as it's called, or one octahedral site within that repeat unit. And so complete occupancy of these holes by the smaller cation would give us a stoichiometry AbO3. And that is the stoichiometry of the so-called perovskite structure, named after calcium titanate, CaTiO3. As I just mentioned, this is the most widely studied structure in materials research, as it exhibits a number of very interesting properties that I'll mention in a couple of minutes. It's built from AO3 close-packed layers. The B cations occupy all of the available oxygen octahedra, and the close-packed layers actually repeat in an ABC-ABC stacking arrangement. In other words, a cubic close-packed arrangement. Now I've put on the next layer on top of the one we started off with. That's in the B position. Let's add on, with cubic close packing, a C layer. So before we do that, we see the available octahedral positions now in the next layer up in blue. Now we'll complete that ABC-ABC stacking, and then we could add another octahedron on top of that. Well, because I'm projecting so many layers, I realize that these octahedral sites, these octahedrally coordinated B-site cations, are not quite so clear. So instead, let's view this arrangement in a perpendicular direction, in the direction of the red arrow, and we'll use our polyhedral representation to focus on the connectivity of those B-site octahedra. And this is the result, or this is the view in that direction, of cubic perovskite. Again, cubic technically refers to the stacking sequence of those close-packed AO3 layers, which are alternating A, B, C in their stacking. Here are those B-site octahedra. We've shrunk down the anions so we can focus on the polyhedral geometry of the B-site cation. And we can see here in this picture that each octahedron is corner shared. And indeed in the perovskite structure, all of those 6 anions at the vertices of the octahedron are corner shared to an adjacent octahedron. There is no edge sharing, there's no face sharing. That actually turns out to be important. So the corner shared BO6 octahedra, all of the oxygen anions at the vertices are shared by 2 cations. And so what was originally for an octahedron BO6, because each oxygen is shared by 2 cations, then the stoichiometry is BO3. Let's rotate this around to show a simpler view of the cubic unit cell. We've done that previously with face-centered cubic metals. We found that the rotation gives us a clearer view of the repeat unit, and this shows the simple cubic unit cell of perovskite. Here are our corner shared B-site octahedra, and in the middle, this is that larger A-site cation that was within the close-packed layers where we started this description. So in this view, that lies in the center of this cube. I mentioned that perovskites have many unique properties, and there really is no other geometric structure that could lay claim to this many phenomena. The perovskite structure is an integral part of the high-temperature superconducting copper oxides, the so-called cuprates, which can show superconductivity up to almost 150 Kelvin. And their discovery in the late 80s caused quite a revolution in the pursuit of high-temperature superconductivities. A number of perovskites exhibit what is called colossal magnetoresistance, in particular manganese-based perovskites. What this means is that one can actually manipulate or mediate their electrical conductivity by applying a magnetic field, and there are many, many important applications that couple to that phenomenon. A number of perovskites show fast ionic conduction, both of lithium and of oxygen anions, and are very important in batteries as cathodes and in some cases anodes, and also in fuel cells. They also show mixed conduction, In other words, the conductivity is both ionic and electronic, so transport of ions and electrons. Many applications here as well for fuel cells and batteries. Many perovskites are very important chemical catalysts, particularly for oxidation and reduction reactions. One of the most recent and exciting areas of materials development has been in so-called hybrid inorganic-organic perovskites, which have been found to show extremely high efficiency in the conversion of solar energy. These new photovoltaic systems are being heavily researched. Most commercial ferroelectric and piezoelectric ceramics, such as barium titanate or lead zirconate titanate, so-called PZT, they are perovskites, a very important class of materials in wireless communications, which are important frequency filters, have the perovskite structures. And these are microwave dielectric materials, such as barium zinc niobate. Well, also, it's even more important because we're all standing on perovskite, as it's one of the most important mineral structures in the lower mantle of the Earth, in particular magnesium silicate. So there's a wide range of chemistries of perovskites, and there literally are tens of thousands of examples of compounds with this particular structure. Indeed, it's interesting to look at a perovskite periodic table, as a structure can accommodate almost every single element in the periodic table. Indeed, the only ones that have not been found in perovskite are shown in white, and actually some of those, such as silicon, can be put into the structure under conditions of high pressure. Not only can it accommodate many different elements, it's also possible for the A sites and the B sites to accommodate multiple ions at one time. And so the A site doesn't have to be one type of larger cation, it could be simultaneously occupied by several. Similarly for the B sites. It doesn't have to be, for example, just titanium, it could be combinations of different cations with different valences. And as long as we charge balance, this structure can accommodate just about everything. But what is it about this structure that makes it so flexible? Well, that chemical and structural flexibility comes back to those corner-shared octahedra. So the whole structure is based on this corner-shared octahedral network, and I'm sure you can imagine that the center of this linkage between the two octahedra, it's almost like a hinge. It can move backwards and forwards. It can bend. In the ideal perovskite structure, it's not bent at all, and so this bond angle is 180 degrees. And I have a perfect cubic perovskite, and the A site cation, which I've made a more realistic size here, fits perfectly in the middle of the cube. What if I put in a cation in this A site that's a little bit too small? If it didn't fit properly, then the structure simply wouldn't form. But in this case, because I have these flexible hinges, the framework can crumple. It can bend, it can tilt to accommodate the cation that's a little bit too small, and therefore stabilizing that compound, that stoichiometry, that structure. This octahedral rotation and tilting is the mechanism through which it's possible to accommodate many, many different sizes of cations and stabilize these thousands of examples of perovskite. And I've just illustrated here on the left the tilting of a pair of octahedra. So now this bond angle from this B through this oxygen to this B, this is not 180 degrees, it's less than that. And here is the correlated tilting or bending of all of the octahedra in the framework, making this cavity in the middle smaller and therefore allowing a smaller cation to be stable in that environment. We could probably have an entire course on perovskites and all of their properties. Of course, we don't have time for that now, but at least I hope that provides you a general introduction into how the structure is built and the key features that enable its stabilization. In a cubic perovskite, we saw the structure was based on cubic stacking of the AO3 layers, which in turn is responsible for and results in the corner sharing of the BO6 octahedra. Just as we have seen in other ionic structures, It is also possible to have hexagonal AB-AB type stacking of the close-packed layers, and this results in a different family of so-called hexagonal perovskites, of which one example is barium nickel oxide. In this structure, the arrangement in each close-packed layer is the same as before, with the second close-packed layer completing the octahedral arrangement of the smaller B cation, clarified here in our polyhedral view. But now, with the AB-AB hexagonal stacking, the third layer is superimposed over the first, and so the octahedral sites form one-dimensional face-shared chains. Shown here is the next octahedral site above, and then we complete the AB-AB stacking. Let's add the third close-packed layer, and we can see here these face-shared octahedra. Let's clarify that in our polyhedral view, where now there is my next layer of octahedra, sharing faces with the one below, and we can see we get these isolated one-dimensional chains throughout the structure. These face-shared chains are clarified in this view perpendicular to the close-packed layers, where we can see the stacking arrangement, AB, AB, and also the face sharing of the octahedra along these chains. Because of the face sharing, it is not possible to tilt the octahedra as we could before when they were corner shared in a cubic perovskite. And so this hexagonal perovskite has very limited structural flexibility, and there are relatively few examples. And the structure does not exhibit the myriad of functional properties that are so characteristic of its cubic perovskite counterparts. There are some other examples of mixed anion-cation arrangements. We saw the AX3, where there's one red for three yellows, and these are the bases of the octahedra that are occupied in perovskite. We can also have other types of ratios of larger cations and anions within these layers. The example shown here, one will find, if we identify the repeat, that the ratio of A to X is 1 to 2. And this is the simplest arrangement, where each cation within the layer is completely surrounded by anions. Here's another example where I have a 1 to 4 ratio of anions to the larger cation. Again, the repeat shown. With the arrangement shown again, I have the larger cations being as far apart as possible, and they themselves are not surrounded by other reds, but exclusively surrounded by anions. So there's no large cation-cation contacts. So both these are possible. And the primary factor guiding this arrangement is the avoidance of cation-cation contact within a given close-packed layer. However, for these two new examples, there are some issues. Let's first look at the AX2 layered cation-anion order. What I've superimposed on this layer is the base of the potential octahedral sites. And in contrast to the perovskite structure, where we could find sites where at the base of this octahedron it was all anions, here that's not possible. Every octahedral interstice in this layer below only has two anion neighbors. And so if I put the third layer on, it's impossible to have any X6 octahedra. It's impossible to have octahedra where if a cation went to that interstice, it would be surrounded exclusively by anions. That's not possible with the AX2 arrangement. Furthermore, if I now build a 3D structure by putting another close-packed layer on top of this one, we'll find, we won't show it, but you'll find if you play around with it, it's impossible to do the 3D stacking that avoids AA contacts. And so this type of arrangement is never seen in ionic systems. But for neutral atoms, actually in so-called intermetallics, where these are not charged species, but neutral elemental atoms, this type of close packing has been observed. For the AX4 close packed layer, we can identify at least the base of octahedra where the three neighbors below the interstice are all anions, and I've shown these in blue. So at least some of these octahedral positions, just looking at one layer, are possible. However, when we put on the next close packed layer, if we make sure this next close packed layer avoids AA contacts, then you'll find that when I put that layer on top of the first, now those potential possible octahedral sites no longer have 6 anion neighbors. They had 3 below, but now we can see for this one there is a red, there's another cation. And so the 3D stacking, if it's going to avoid reds being nearest neighbors, it simultaneously eliminates the possibility of having any octahedra where the smaller cations would be exclusively surrounded by anions. And so in that sense, the AX3 perovskites were kind of unique, again, in that this type of in-plane arrangement was somewhat unique in avoiding cation-cation contacts within and between close-packed layers, and simultaneously allowing some of the interstices to have 6 anion neighbors. For the AX4, there are no ionic examples, but again, this type of pattern of ordering can occur if all of the atoms are neutral, for example in metallic alloys. Well, it might not be quite the same as a day at the beach, but I really hope you enjoyed the video anyway.